During this session, we will look under the hood of WebAssembly, and it will be led by Sohan. Sohan is a lead developer advocate based in Netherlands. He started his career as a developer building custom mobile apps. Since 2013, he has been in developer relations space in companies such as Amazon, GupShop, and InMobi. And the core of this talk will actually focus on what WebAssembly module is and how it is executed. So please welcome him.
Hello, check. Thank you. I assume everyone can hear me. Well, thanks for attending this talk. My name is Sohan. I'm a lead dev advocate at OddZ. And this is my second time in both Belgrade and at HeapCon. So I'm excited. I love this conference. So thanks for having me. So I'm talking to you today about what actually is WebAssembly. So we're going to do a deep dive to see how it works. I'm sure most of us have heard of WebAssembly or may have used it a little bit. But the key takeaway from this talk, hopefully, is how WebAssembly works and how you could maybe use it in both the client and the server side. So if you get that at the end of the talk, I've done my job. So I'll give you a little bit of history. So in 2015, some of y'all may have played this game called Angry Bots. Maybe I'm dating how old I am, but I remember seeing this game making some waves back in 2015. But this is actually historic for two reasons. One is the same game was used many years before to test out WebGL on the browser. And then as a reference to that, basically, this thing called WebAssembly was invented and launched in 2015, and they made this game in WebAssembly to test out and show the power of WebAssembly. Right? So a bunch of companies that make browsers, like Mozilla and Google and Microsoft, got together to come up with this thing called WebAssembly, and they demoed it using this game. But what is it exactly? Right? So as the name suggests, WebAssembly was meant to be for the web. And the interesting thing to know is that it is a bytecode format. Right? So that's the first line there. Now, computers understand binary, zeros and ones, but sometimes there is something that's intermediate, like an intermediate representation, again in a combination of numbers and words, that's called a bytecode. This bytecode is understood by things like a virtual machine that is designed to understand that bytecode. So these people making these browsers were like, hey, every browser runs like JavaScript. That's all that's happening. What if I could run a Rust or a Python or a Go program in my browser? And what if that same program could run on different browsers, on different operating systems, on different architectures? Right? And they were like, I should be able to code in all these different languages, compile it once, run it anywhere. Right? And that's where the idea of WebAssembly was born. And the idea was, it could run on all of these different places. And you'll hear people say WASM, as you see there, W-A-S-M. WASM and WebAssembly are the same thing. It's just a different name. So how it looks like is this. You can write code in a bunch of different languages like C, C++, but even Python, JavaScript. And you compile it to something called WebAssembly, which is the bytecode format. That is executed on a runtime called a WebAssembly runtime. And these runtimes are designed to be run anywhere. So any operating system, any architecture, Raspberry Pi, cloud, whatever, a WebAssembly runtime should be able to run it. Now, a few of y'all might be thinking, wait a minute, this looks a lot like Java. Right? In Java, you write something to Java bytecode, compile it to a Java virtual machine, which can run anywhere. And you're right. In theory, that is sort of the idea behind this, where you write once, compile once, and you can run it anywhere. So I'm here to break down what these two things actually do, starting with the WebAssembly module. Right? So what does a WebAssembly module look like? Well, this is the most basic WebAssembly module. Knowing my programming skills, I would probably make a syntax error even here. But this is a basic WebAssembly module. Two things to know when it comes to a WebAssembly module, and these are two new terms, which is the terminology of guest and host. So how WebAssembly was designed was any module is called a guest WebAssembly or guest WASM module. And this is our guest WASM module. All WASM modules run in something called a host, which is the runtime. So one host can have multiple WebAssembly modules. To give you an analogy, think of it as hotel rooms. So when you go into a hotel, you have access to your room. You don't have access to other people's room. That's how a guest WebAssembly module looks like. There are multiple different modules that can't access each other, but they can access shared spaces in the host runtime, like how when you're in a hotel, you can access the gym or the restaurant. Yeah? So that's the idea behind having multiple guest WebAssembly modules in one host. So what can you do in this WASM module? Well, you can actually have functions. Right? So if you look at this function, line number 2 is to add 2 numbers. Yeah? Simple left-hand side, right-hand side, it says LHS, RHS. In line number 6, it's just a function to increment a number by 1. You will see line number 8 that says const 1. So it's just incrementing a number by 1. So how that looks like is this, where that WebAssembly module has 2 representations. A text representation, which you just saw, which is human readable, and most importantly, the WASM representation, which is this bytecode format. So this is what bytecode format actually looks like. The text representation essentially uses S expressions to be passed. Right? This is just a binary tree and a way to represent the text expression. So as you can see, line 1 is module. You have module there. Line 2 and 6 are 2 functions, add and +1. So you have the 2 functions here. And then, of course, you have each line in the text representation. We're not going to worry too much about this. We are going to worry about how it looks in this representation. So there are 2 functions to add 2 numbers and to increment a number by 1. All of this is contained within the WebAssembly module. They can call each other. Now, I'm a user. I'm like, hey, I want to add 2 numbers. I should be able to call that function, right? Well, not quite, because it is essentially, just going back here, sorry. It is essentially sandboxed so that nothing can access this unless you specify access. Now, how does that add function work? Well, WebAssembly runs on something called a stack machine. If you've studied computer science or if you've looked into the theory behind computer science, you'll know a stack machine it's a stack where you add things in and then you can pop things out of a stack. That's a data structure to represent something. And WebAssembly is an example of a stack machine. So we have this program here. First line, function add, you get 2 numbers and you send a result. Line number 2, you get the left-hand side. Line number 3, get the right-hand side. Line number 4, add it. So how does this look in a stack machine? So we get the first parameter, and we add it to the bottom of the stack. We get the second parameter, and we add it to the stack. So what happens now is you want to add the 2 numbers, and you also want to be very memory efficient. So what essentially happens is those 2 numbers are pushed out of the stack, and the result of line number 4 is pushed here into the stack. Right? So again, this is being a little more performant and saving on memory, where you remove those 2 from the stack and put the result right here. And then this result you get with what remains in the stack. So any computation in a WebAssembly module, this is how it works. Yeah? And typically, the functions in a WebAssembly module are things like computation, small loops, if statements, and so on. But they can't write to anything. They can't access files, etc. But we'll get to that. So like I said, this is a security sandbox. So as a person who wanting access to any of these functions, you don't have access. Right? They're like, nope, not allowed. By default, everything is security sandboxed. So we need this to be useful for us. So essentially, WASM lets you export functions as well. So you're like, hey, I'm good at adding 2 numbers. Other people might want to add 2 numbers. So let me export that function, line number 6, so that other people can use it. So this is how it looks like. You have a function in the WebAssembly module, which again is sandboxed. But that function is exported into the host runtime so that other people can access it somehow. So in this case, I can invoke that add function, and then the rest happens. Now, I want to print the result, but a WebAssembly module can't do that. Luckily, you can also import functions from different places. So in this case, you see line number 2, I'm importing a console.log from somewhere. And in line 3, I'm printing the number. And line 4 and 5, I'm just getting it and calling that print function. Going back to that diagram, this user supplies a console.log print. right? I'm supplying a function that this WebAssembly module needs. So it imports that function. We can put all of this together and actually call the function and print it out as well. Now we come to the topic of memory. What if you want to store the result of that addition into memory? WebAssembly has something that's slightly different from how typically people or programs use memory, and it has something called shared linear memory. That's a mouthful, so let me break it down. We all know what memory is. I won't explain that. Linear is interesting. So sometimes in computing, when you ask for memory and it gets it from different addresses, it's not a contiguous block. It's not from block, like say 1 to 100. You get different addresses in your memory. WebAssembly was designed so that you have a contiguous block of memory. And that memory is shared, hence the name, shared linear memory. It's shared with the host runtime. Yeah, you remember guest and host, it's shared. What does that look like in code? Well, if you look at line number 3, it says imports this from memory, memory 1. What that essentially is doing is it's importing what's called one page of memory, right? That's the memory 1 there, which is equal to about 64 kilobytes if my memory serves me right. And essentially, it's getting that from the memory. It's saying, give me 64 kilobytes of memory. And then in line 4, starting at the 0th index, I write hello world. Yeah? So it's contiguous. Starting at 0th index, I've written hello world. And then when I call hello world in line number 5, I'm saying start with the 0th index and go 14 characters, which is the length of hello world, and then call my console.log, which was given to me by my user. So let's see how that looks. This user supplies the function console.log. We saw that earlier. It invokes the exported hello world function, which goes into my guest WebAssembly module. But what is important you need to see here is that data hello world is initializing into the shared linear memory, which can also be read by the console.log because it is shared linear memory, right? So the idea of giving you all of this is how it's working under the hood when you call a WebAssembly module. And all of these decisions about shared linear memory, about a virtual stack machine, about a limited instruction set, all of this leads to good performance, right? Because it was designed ground up for performance. Now, we have a WebAssembly module. It's doing all of these cool things. How does a runtime actually host or execute that WebAssembly module? There are a few steps, and some things, again, are interesting. So there are 3 basically phases, right? You first start with the decoding phase, where you have your WebAssembly module, and there is some decoding to get the internal representation that the runtime can understand. Now, this is a bookkeeping step, right? It's just to make sure that this is a correct WebAssembly module, it follows all the rules, and it's not going to error out later. The second step is validation, where, again, there are checks to see if it's a valid internal representation, if it's accessing memory that doesn't exist, if it's well-formed, etc. The interesting thing here is decoding and validation can happen at the same time. So if you have a 10 MB WebAssembly file, it does not have to fully be decoded before being validated. As soon as the first byte is decoded, that can be validated, which makes it great for streaming purposes, but again, also makes it performant, because you can do this all simultaneously. And once that's done, you sort of instantiate that WebAssembly module, and you invoke it, which runs the WebAssembly module within the runtime and gives you the result. Right? So that's how a WebAssembly module works, and then a WebAssembly runtime actually looks at this WebAssembly module this way. There are a few popular WebAssembly runtimes out there. Most modern browsers like Firefox, Chrome, SpiderMonkey, all these engines, Chromium, they support WebAssembly. So you can run JavaScript and WebAssembly in your browser right now without any extension updates, etc. There are other runtimes such as wasmtime, which are also like an industry standard WebAssembly runtime. So say you want to run it in a certain place, you can use WebAssembly runtime such as wasmtime or even wasm3 to run a WebAssembly program. Okay, so the question I get asked the most is, all that's fine. I don't want to know how it works under the hood. I want to know how, when I write like a Rust code, it's converted into a WebAssembly module. What does this sort of look like? So again, without going too much into the depth, because I think that's an entire talk altogether, there are potentially two ways this could work. In terms of languages like C, C++, Rust, these are slightly lower level languages, right? They are lower level languages. They don't need an interpreter. They just have one compilation step to something a computer understands. So those actually make it a little easier to compile to WebAssembly, and they have better support. Because you can start with a language like C, write a C program, and then use some industry standard tools such as CLang, LLVM, and Mscripton. And what that does is it converts that into that internal representation, which is then converted into that .wasm file. Once you have the .wasm file, this could run on any WebAssembly runtime, which could run anywhere. Right? So this process is fairly straightforward. It's faster. There's better support, and so on. Where I think it gets interesting is what about interpreted languages like Python and JavaScript? So languages like JS, Python, they need an interpreter to convert it to something which is then compiled, and then a computer understands it. So this, I feel, is it's a very smart way of doing it. So the Python interpreter itself has been compiled to WebAssembly. Right? So some very smart people have actually done that. They've taken the Python interpreter, like CPython, compiled that to WebAssembly. So when you're writing something in Python and you want it in WebAssembly, your source code and the Python source code that's compiled to WebAssembly are snapshotted during execution and then run into your WebAssembly runtime. I think that's pretty smart and pretty cool, where you take the interpreter written in WASM, you take your source code, you mix the two, it's a just-in-time snapshot, and then that's executed to run on a WASM runtime. There are other methods also people are trying out where you can sort of transpile Python source code and not use the interpreter itself, so you transpile it to a lower level language, which is then executed. But these are different ways, people are trying to write code in an interpreted language and then convert it to WebAssembly. So I'll show you a small demo of how we at OddSed use WebAssembly. There's not much of the WASM stuff that you can actually see, but I'll give you a sense of what it looks like. So at OddSed, we have this thing called a playground schema. And we essentially do permissions at scale. Right? And to test that out, we have a product. It's completely open source. So essentially, still loading. Essentially, think of it as if you want to do authorizations like in Google Docs, you have a schema. So you have, say, a definition user. You have a resource, like, say, a document. So you could have a writer. You could have a viewer. And the permission to write is only with the writer, and the permission to view is with the viewer and the writer. All right? This is just how it looks. I can actually add, like, one user here, perhaps. Let me just show you a demo. I will say resource is blog. Okay, so this is a blog, and writer is user Sohan. Right? So how to read this is user Sohan has permissions to write to the blog, but we'll add another user who has permissions only to read to the blog. Right? I'll say user, and I'll say Jim. All right, that's it. And I can actually check this based on, let me do this, resource, blog, view. So who can view this thing? Oh, I think there's a... If this doesn't work, it's fine. Yeah, it should be fine. Sorry, my bad. Thank you. Yeah. So when I say view, both the writer and the viewer have access. But if I say write, only my name should come up. Right? There we go. So essentially, this is a simple open source thing to test out schemas. So how this works is it's actually looking at a live database called SpiceDB, which is evaluating these permissions. Now, how we had implemented this earlier was there was SpiceDB running in the cloud, and every time someone made any of these assertions or relations, it would go to that SpiceDB in the cloud, make a check, and send it back. But we were like, hey, there can be network latency. We'll have to maintain that code in the cloud. There are all sorts of things. But is there a way to get a local version of SpiceDB running in the browser itself? So SpiceDB was written in Go, and luckily Go has great WebAssembly support. So we were able to compile SpiceDB into Go and load it into the browser itself. If I just do like a quick sort of inspect element here, you can actually see the WASM files being loaded here. These are like a different bunch of WASM files. So we have SpiceDB that's compiled to Go, that's running in the browser, against which these checks are being made. Honestly, this is a pretty great system because we actually were able to build a real implementation of SpiceDB without relying on something that's server-side. So we don't have to maintain that. We don't have to keep that running. There were two benefits of this. Right? One is we were able to compile the SpiceDB Go source into WebAssembly. And the unintended or surprising consequence was any non-JavaScript implementations between clients and servers are now possible because it is compiling to WASM. And the cool thing was we actually saw the request latency decrease by 90% because, well, it's all happening in the browser. There's no like network latency. So honestly, for a lot of client side where you want to load something and let the user interact with, I would highly recommend WebAssembly, and all of these companies use it in parts of their front end. Like I know Figma and Adobe uses WebAssembly and in some of their in-browser editors because of how performant it is and because of how lightweight it can be. So do check it out. Just to give you a recap of the things that I spoke about, right? WebAssembly was designed to be polyglot, where you code in a bunch of languages and it's supported. It's designed to be secure. There is a security sandbox by default, which denies everything unless you specify. It was designed to be portable, which means it's cross-platform, cross-OS, cross-architecture. And it was designed to be performant, near-native execution speed. It was also designed for the browser, but everyone was like, hey, all of these things actually make sense on the server side. Think about it. On the server side, you want security, portability, and performance. That's what we want. So in 2019, something called WASI was implemented. Now, for something to run on a server, you need access to server things like files, networks, system clocks, random number generators. Otherwise, there's no point of running something server-side. So people were like, hey, what if we could take WebAssembly and make it run on the server side? And essentially, a new standard called WebAssembly Systems Interface, or WASI, W-A-S-I, was introduced. Now this, I think, and maybe I'm a little biased, but I think it's very exciting because it allows you to run WASM outside the browser. You don't need like a browser to run WebAssembly, and it gives you access to server things like clocks and file systems and random numbers, etc. And it includes the security sandbox to include files and input-output. Right? So you're still preserving the security of WebAssembly, but by running it on the server side. Some advantages of running it on the server side, like I said, it's portable. So imagine you have an API server written on WebAssembly. You can swap out the underlying infrastructure, and it will still work. You don't have to make any changes to your code. It's very lightweight. A Hello World WASM app written in Rust, which I will show you now, is a very small OCI artifact. And this makes sense at scale when you want to design for something that is very lightweight and you want to save on performance and time and storage, etc. We spoke about the sandbox, about security, why it is security sandboxed by default. And of course, WebAssembly components are designed from the ground up to actually be performant, right? To have performance. So these are some of the reasons why WebAssembly on the server side is gaining some traction. I'll show you a small demo. I'm going to write a simple Hello World app, and I'll write it in Rust. But honestly, you could write it in pretty much any language. It's using an open source product called Spin from this company called Fermion. Check it out. Essentially, it's the developer experience around building server-side WebAssembly apps. So let's see how that goes. again, github.com/fermion/spin. I've already installed the spin CLI, so I'm just going to show it to you on terminal. I do spin new. Now, how the idea of WebAssembly on the server side is essentially, how many of you here have done serverless computing, like Lambda or Azure functions for you all? Yeah, well, the idea is something similar, right? Where you have a WebAssembly function that's running somewhere, like in the cloud, and you get an event to that function. It does something, and it sends a result back. So event-driven computing. And if you see here, on the left, you will see the different events that you can actually run. Most of them are HTTP calls, but it could also be something like a Redis call. There's a change in your Redis database, or something's updated, so it makes a call to a function that's running in the cloud. On the right, you will see things like C and Go and JS and PHP. Those are all the languages you can write code in, which is then compiled to WebAssembly. Yeah? So it's very polyglot in the sense most languages you're coding in are supported in WASM. So I'll pick Rust because I hear all the cool kids are writing Rust now. I don't know. And let's call it heapcon. Description. You'll see something that says HTTP path. This is a path like a URL. So by default, it is default. So any ping to that URL will run that function. But you can have different functions. Like you can have /checkout, which reaches one function, /by that reaches another function. And here's the cool thing. Those two functions can be written in two completely different languages because they're both compiling to WebAssembly. So you can have /checkout in Python and /discount written in Go in the same app. Yeah? And that's one of the cool things about WebAssembly. I will use the default for now. And let's do this. Cool. I'll just take you through the code, which honestly is fairly straightforward. Yeah, so this is what it looks like. If you're familiar with serverless or event-driven computing, this will look very familiar with you. You can see in line 6, there's a request coming in. And yeah, that's the request right there. In line 7, you're just printing to the console. And typically below that, you will do some sort of processing, right? You will do an API, you will do some computation, and then you just send a response back. So simple, there's an event that happens. There's a request that comes into this particular function, and then you do something, and a response goes back. Right now, it's just a hello world. It says hello Fermion, but let's change this to hello heapcon maybe. And I will go back to my terminal. And with 2 commands, we can have like a local API server running on our system. I'll do spin build, which basically builds the app. The first time you run it, it takes like maybe 10 seconds, but after that, since Cargo has built all of the dependencies, it's much faster. Yeah, it's built now. And I will set up a local server running on my local host. Yeah, so I can just do a curl command to this, curl -i. Yeah, and it says hello heapcon there. So in like 2 minutes, I have a local API server for testing. And you could deploy this to the cloud, or you can have this running somewhere. And you have like a serverless function that's actually up and running. So I think in terms of having things for very lightweight computation, WebAssembly makes sense. So the big question, right? Server-side WASM, what is the advantages? Well, if you've worked in serverless computing, you know that serverless right now has a couple of problems. The one big problem is this concept of a cold start. So essentially what happens when you use AWS Lambda or Azure functions is an event happens, and then it goes to AWS or Azure's cloud, and then it has to start up that Lambda function. Now, that takes some time, usually between 250 to 500 milliseconds, because that function is not running. It's not been used until that event actually hits it. And that latency is called a cold start. Now, at scale, at critical applications, you want to reduce that as much as possible. So what people actually do is they keep the functions warm. Right? They keep sending pings to the function so that it doesn't have to start from 0, because when it scales back, it takes time to start up again. With WebAssembly, because it is so performant, that cold start time is reduced by orders of magnitude. Right? You don't have to do any tech to really change that cold start because of how performant WebAssembly is. And you can try it out for yourself and see any benchmarks. That cold start time is reduced to like less than a millisecond. So that's one. Two is, in the ecosystem we have right now, if you're doing serverless computing, you are locked into either using AWS or Google Cloud Platform or Azure functions. You can't have a Lambda function talk to an Azure function talk to a Google Cloud function. But again, if you use server-side WebAssembly, you can actually be vendor agnostic, right? And maybe host it in your own places because, again, this is an open standard and we're using open source tools. It could also change how we think about containers, for instance. Any Kubernetes containers users here? Few of y'all, not too many, okay. So with containers, the one big problem in the industry right now is the concept of utilization. Because we have these containers running in virtual CPUs in the cloud that take memory, that take like network space and computation, but the utilization of that container is actually very low. 2 years ago, I spoke about sustainability in cloud computing on the stage, and containers not utilizing their resources is absolutely not sustainable. What could change that is having these lightweight WebAssembly functions in a container, where instead of maybe running 3 pods of a typical container, you have a lot more WebAssembly functions densely packed within one container. Now, this all sounds very good, too good to be true, right? What is the reality of it all? The thing is, this is very new. WASI was introduced in 2019 as an idea, so it's still evolving, which is why few things need to improve or be in place before this can get mass adoption. One is the language ecosystem itself needs to evolve. I gave you an example of Python, right? In the real world, though, lots of people use Python with their custom libraries, and that might not have a WebAssembly representation. Sure, something like NumPy or Pandas, they have WASM representations, but your custom library might not. So in the real world, it becomes difficult to port that code into a WebAssembly module. At the same time, there's no wide adoption just yet, so it's a chicken and egg problem. Everyone might do like a POC and is like, wow, this is making a big difference. It's faster. It's going to save me a ton of money. But I don't know how it will be in the real world. So everyone's sort of waiting, I guess, for someone to actually take that plunge. And at the same time, we don't have widely used package registries, for like how Docker had their Docker Hub and OCI. So, or AWS has their marketplace where there is a place you can go to actually start a business. So some things need to fall into place in the ecosystem, and then we might start seeing WebAssembly being used on the server side as well. Okay, so next steps, hope that made sense. If you're interested in how the demo I showed you with the playground, if you're interested in reading a lot about that, you can check it out. There's nice technical details about how some things in the code were not supported in WebAssembly, so we had to remove it and port it. You might find that fun. For the Kubernetes people here, and I know there aren't too many, at KubeCon earlier this year in Paris, there was a launch of this open source product called spincube.dev, which is to allow you to put WebAssembly on Kubernetes. It was developed by SUSE and Microsoft and Fermyon and a couple of other companies. Again, if you're in that Kubernetes cloud-native world and are interested in checking out WebAssembly, I would check out spincube.dev, fully open source. And the last thing that I actually want to talk to you about is something that is very interesting in this world of WebAssembly called the component model. Now, I told you earlier how you could have one program with modules written in different languages. Now, what if you could combine those modules into a new module, right? And that is the idea behind the component model. It's very much live. It's in its early days. But the idea is, say you have a Go program, which does something, and you have a JavaScript program that does something. These are two independent WebAssembly components, and those could be combined to form a new component. So in the future, software development could actually be very modularized, where I'm writing a program, and say I need a date parser, and I don't want to write my own. But I've written a program in Python, and I'm like, OK, there's a good Go program that passes dates that is fast. I can just use that component into my program as a modular way of coding, right? And it opens up very interesting ideas for things like CI/CD, for security, and for just generally thinking about programming in general. So do check it out. It's good to read about it. It's nothing you can implement today in your big enterprise because it's so new, but important to know about. Anyway, that's all the time I have for. Hope you learned something new. I'm here for questions, and feel free to connect with me on LinkedIn as well. Thanks for having me. Thank you. We have 7 seconds if anyone has questions. Yeah. Yes.
You mentioned that modules are sandbox. How can they communicate? You mentioned that linear memory, but is that like you can write bytes there, or is there something more?
Yeah. So the question was, how do modules sort of communicate with each other? Yeah, I think you pretty much answered one half of the question, which is they can communicate in 2 ways. One is by export and importing functions, and the other is through the shared linear memory. That's the only way, but you have to explicitly call that out. To access an API, to access a file, all of that has to be explicitly allowed for a module to access it, both ways.
Do you get types when communicating, or you have to marshal everything?
Oh, OK, good question. Do you get types when communicating? Well, WebAssembly has only just 2 types, like an int, I think 32 and 64 or something. So it's sort of standardized that way, yeah.
I'm sorry, can you just repeat the question because we're recording, so you didn't have just the microphone, so. Just to
Hello,
have it
great
recorded.
presentation, thank you. So the question was, how do modules communicate, basically?
Thank you. Sadly, we do not have enough time for another question, so please find him on the break and ask anything else. After this, we have Alex Shoshabnev, and he will talk about AI agents, so that's it.